Let's extend the idea of acceleration, velocity, and position from the last video and start with acceleration and see if we can't find a position function. So since acceleration is the second derivative of position, we're going to need to take two antiderivatives. And each time we're going to get a plus c, and we're going to need some information to try to turn that plus c into an actual number. So in this case, I've chosen the acceleration to be the acceleration due to gravity in the metric system, negative 9.8 meters per second squared. I've set the initial velocity to be 0 and the initial position to be 100. Essentially what we're going to do is develop a position function that will tell us the position as a function of time for an object that is dropped from a height of 100 meters. And it'll give us that height for any time t while it's dropping. So let's see what happens if we do that. We start by taking the antiderivative of acceleration. That's going to give us velocity. And that is going to be negative 9.8 t plus c. We know that velocity at time t equal to 0 is 0. So that's going to be negative 9.8 times 0 plus c is equal to 0. That says c is equal to 0. And therefore our velocity function is just negative 9.8 t. Antiderivative of velocity is position. So s of t is going to be negative 4.9 t squared plus c. We know that when t is equal to 0, that's negative 4.9 times 0 squared plus c. We're going to get 100 for our height. That says that c is equal to 100, and therefore s of t in this case is going to be negative 4.9 t squared plus 100. For those of you that have taken physics and you've seen some of these acceleration, velocity, and position functions before, especially the kind where you plug in a v sub 0 and an s sub 0 for initial velocity and initial height, this is where those equations come from. Essentially the plus c that we pick up in the first antidifferentiation is v sub 0, or initial velocity, and the c that we pick up in the second antidifferentiation is s sub 0, or the initial position.